first I want to discuss where we are in the semester. We have 3 weeks left, I think, right? 3 weeks. We're 5 weeks in with 3 weeks left. So we're on the home stretch, as they say in horse races. We just got a little bit more work to do. First of all, the obstacle we have coming up is exam number 2. Exam number 2 is going to be on Wednesday. I'm going to post it on Wednesday. You can get started on it, but I'll give you at least a few days to do it. As an exam 1, you'll have 2 opportunities to take it. First one, after you submit your first opportunity, you'll be able to see which questions you got wrong. You won't get the answers, but you'll at least be able to see which ones you got wrong. And then you'll on the second opportunity, you'll be able to start again all over again. Of course, you should record your answers so that, like, the ones you got right, you get them right again, because Blackboard will not let you carry over those answers to a new test. So it's non-cumulative. So it's only going to cover basically the material that we've covered since the first exam. Included in that is going to be confidence intervals, because they kind of tie in with the t-test. The t-tests itself, single sample t-test, independent samples t-test, one version with equal variance is assumed, other version with equal variance is unassumed. I don't think I'm going to ask you to calculate it from scratch. Most likely, I'll give you a data set or some output, and you'll be able to use SPSS to complete the t-test. We'll also cover analysis of variance. You may have noticed that I flipped the order for chi-square and analysis of variance on the syllabus. We were going to do chi-square last week, and we're going to do analysis of variance today. I flipped those because it makes more sense, since analysis of variance is just another way to compare means of different groups. In the case of analysis of variance, more than 2 groups. It's made more sense to do that along with the t-test than to kind of flip back and forth on that. So today we're going to cover chi-square. Now, this material is not specifically going to be on this exam. So it will only be up to what we've covered up till last week. On Wednesday, I plan on doing an online review session. So I'll review confidence intervals, t-test, chi-square, so on and so forth. And you can use it as preparation for the exam, for taking the exam. And maybe after you take your first effort, if you see something maybe that you had a problem with, you can go back and rewatch the review session. So I would recommend that if you have an area that you have some concerns about, when do I use equal variances, unequal variances? How do I calculate the confidence interval for a proportion, and so on and so forth? If there's something specific that you have concerns about, put it on the discussions board. I don't know if I have it right now, but if it's not there already, I will put up a thread for questions related to material you want covered in review sessions. So post it there so that we can all get the benefit from any information that we wind up sharing. Okay, so, and as I said, Wednesday will be a review session. We'll do that strictly online. Okay, so you guys can tune in at that time. I will record it, and we will, you will be able to watch it later on if you're not able to tune in with us. I'm going to do it at class time, even though I'm not going to do it live, not going to do it here at school. I will do it at class time. So presumably anyone who wants to attend it probably kind of has, maybe, if not, maybe is more likely to have those hours tucked away in order to be available. If not, don't worry about it. We'll record it and make sure it's online within a day. And but that's particularly, in that case, it's particularly important that if you have questions, that you make sure you get them into the discussions board so I can address them, even if you're not present for the review session. Okay, so any questions on that so far? I'll wait a few moments to deal with the lag and see if anybody has a posting on the chat box. Okay, I will assign a homework on chi-square. I'm going to give it a long enough lead date. In other words, it won't be due until after the exam, so you won't be distracted by you having to do the assignment for chi-square until after you've completed the exam. Okay, I don't see any chatter on the chat box, so I'm going to go ahead and dive into this stuff called chi-square. Okay, so to discuss chi-square, let's talk about what chi-square and odds ratio and relative risk are not. They're not a mechanism for comparing numerical variables. In other words, they're not meant for comparing the mean of one group to the mean of another group, or the mean of one group to the means of 4 other groups, or so on and so forth, as we would be working with numerical variables with t-tests and analysis of variance. In this case, we're going to really diverge. We're now going to look at, well, what if instead of numerical data, we're dealing with categorical data, right? Categorical. Okay, also, we could call it nominal data. Same thing, right? Categories, names, basically the same thing. Okay, so what kind of data might we be looking at? Well, we may be looking at information that is like either a true or a false, right? In other words, or a yes or no. For instance, is a person diabetic or are they not diabetic? That's a categorical variable, right? Category is disease or no disease. So the variable is diabetes, and one value we could have is yes or no. The other value is no. We could have a series of categories. A categorical variable that has more than 2 values. That is two values. It's binomial, right? It's 2 values. You can have more than 2 values. So for instance, in ethnicity could have that variable is nominal, right? It's a name, it's a group or a name or category, right? It could have many variables: white, black, Hispanic, Asian, Pacific Islander, so on and so forth. So you could have many. In New York, it could have 50 values, right? So even though it could have many values, and even though we might input or identify these values in SPSS as numbers. In other words, we might say 1 is diabetic and 2 is not diabetic. Even though we're using a number to represent it, it's still a name or a category, right? Ethnicity, we might be using many numbers to represent the different ethnicities, but it's still, those numbers represent the values of those categories. So they're not really numbers, just being used to simplify the input of the data, but they are still nominal categorical data. So now let's say that we're in a situation where the data that we're examining is only categorical. So for instance, let's say that we're interested in knowing whether or not HIV status is associated with IV drug use, right? Well, let's say HIV status is either you're positive or you're negative. And what about IV drug use? Well, we could limit the definition of that to either you're a drug user or you're not a drug user. Okay, you're not an IV drug user. Okay, IV drug user, right? So we have 2 categories for IV drug use and 2 categories for HIV. I chose a couple of categories or nominal variables that I'm going to work with that only have 2 values, but we can work with many more values in each of the 2 categories we're comparing when we use chi-square. But we'll get into that as we progress. So I'm going to start with a fresh sheet of paper. Okay, and I'm gonna keep this conversational for now, rather than PowerPoints and a lot of complicated calculation. Actually, you're gonna find that this is really one of the simpler kinds of statistics, more direct forms of statistical tests that you're gonna come across. It's gonna be kind of, I think, intuitively obvious what this means, how this works. Hopefully, if I explain it well. So I'm going to set up a contingency table. Remember, contingency table, we used them when we were discussing diagnostic tests earlier in the semester. Okay, so in the rows, I'm going to put the exposure. So for the description I just gave you, the exposure is going to be IV drug use. IV drug use, yes, and IV drug use, no. Okay, so in our rows is the category or nominal variable IV drug use. In our columns is going to be the result or the outcome, which is going to be HIV status. Right? That's that variable, and it's either going to be HIV positive or HIV negative. Okay, so let's say that we sample a population in a rehab center. Right? Okay, and in this rehab center, we randomly select 200 patients. Okay, so we're looking at whether or not there's an association with in IV between IV drug use and HIV in rehab centers of this type, right? And we're sampling a group of 200 people in that. Randomly select them. And we find out of those 200 people, we find that 40 of them are HIV positive, right? So what is our prevalence for HIV in this population? Okay, we have 40 out of the 200 that have HIV. What's the prevalence going to be? Anyone want to chime in on that? Right, it's going to be 40 out of 200, right? 40 over 200, right? And what's that going to be? That's going to be 20%, right? So 20% of this population, the sample from this population, is HIV positive. That's kind of a high percentage, right? But remember, this is a population that is likely to be have a higher prevalence of HIV than the general population, let's say. So this represents maybe a number of rehab centers, which has a population of tens of thousands, for instance. We're sampling 200 of them. So it appears that the prevalence of HIV in this population is 20%. Okay, so now let's say that I find out that 50 of the people in this study are IV drug users or have been IV drug users, and 150 of those people are not IV drug users. Okay, so we have 200 people total, as we mentioned, right? And 50 of the people out of those 200 turn out to be IV drug users, and 150 of them turn out to be non-IV drug users. Okay, so out of the 200 people, how many people are going to be HIV positive? Well, out of 200, the number of people, the total in the columns HIV positive, is going to be 40 people. Right? We already know that at 40 out of 200, and 160 people are going to be HIV negative in this population. Okay, so now let's look at this a little closer and say to ourselves, okay, so if I have 50 people who are IV drug users and 150 people who are not IV drug users, and there's no association between IV drug use and HIV status. They don't have anything to do with each other. In other words, could have been being left-handed in HIV status, for instance, instead of IV drug use. Ignore what we know, and just say to yourself, well, what would I expect if there's no association between IV drug use and HIV status? Well, how many of these 50 people would I expect to be HIV positive in that case? Well, the prevalence for the population is 20%. So I would expect 20% of these people to be HIV positive. So with 20% of 50 is 10 people. And what about these 150 people? How many of those, if the prevalence is 20%, and it doesn't matter whether you're IV drug user or not, out of these 150 people who are not IV drug users, I expect 20% of them to also be HIV positive. So 20% of 150 is 30 people. And that makes sense because it adds up to 40, right? The 40 people in our population. So how many are here? That's 40 is HIV negative, and 120 are HIV negative here. Well, that seems pretty straightforward. And if we did this study and we found exactly this result, right, what would that tell you? That would tell you we were cheating, because it seems very unlikely, even in a perfect world, that if we got that, we would get exactly that result, even if it was 20%. And IV drug use had no impact on HIV status. But we would expect pretty close to this, right? Like 9 and 31, or 11 and 30 and 29, or something like that in these two, in the first column, and so on, right? So we'd expect to be pretty close to that. This is what we would expect. So we call these our expected values. Okay. So now what if I told you that we now took this, let's take this table again. I'm going to draw it again. IV drug use. Yes. IV drug use. No. HIV. Yes. HIV. No. And we know there's 50 of them and 150. And whoops. And we know that there's 40 people out of the 150 that are HIV positive, and 120 and 160 who are not. Well, let's say that when I really actually asked each individual person, and when we have the SPSS data, we would have this as one column is HIV and the other column is IV drug use, and we would have 1, 1, 2, 1, 1, and 2, 1, 1, 1, 2, and so on and so forth. And that would represent whether they are HIV, each individual person, what's their HIV status and what's their drug use status, right? We would then know that for each individual person. So now if we put all this data together, figured it all out, and it turned out that the number of people that are IV drug users that wound up being positive is not 10, but it's 15. Well, that would make this 35, right? Well, if these are 15, then the number of people left that are IV drug users, this must be 35. Excuse me, yeah, 35. I got it backwards. Hang on a second. I had 25. This is 25, and this is going to be 125, right? I think I got that right now. Okay, so this is the values that we observed. These are our observed values. Okay? So here's our expected values, and this is what we actually observed. Okay, so now I'm going to say to myself, okay, so now what am I looking for here? What I'm looking for is to see if there's an association between this variable and this variable. Okay, so I'm going to start out. I'm going to create a null hypothesis. I'm going to open up the page over here to work with. Hopefully, it'll work. Try again. We're going to get the page. Okay, I'll redraw this. Okay, it depends on you to help me remember. Okay, my expected values and my observed values. Okay, this is 50 and 150 and 20%. This was 10 and 30 and 40 and 20 and 40 and 160. And over here we have, and this is HIV positive, and this is HIV negative, and this is IV drug use positive and negative, and IV drug use positive and negative. And let's see what we got here. Here we had 15 and 25 and 35, and to add up to 50, and 125 to add up to 150. And again, still 40 and 120 and 160. Okay, observed values and our expected values. So now let's think about this now. My null hypothesis is, as it is always, is that there's no association, there's no difference between these two possible outcomes. So my H null is that there's no association between HIV status and IV drug use. And my alternative hypothesis is that there is an association. One of them, IV drug use does impact on the likelihood of having HIV. There is an association, is my alternative hypothesis. Okay, so if my null hypothesis were true, what would I expect here? I would expect for my expected values to be similar to my observed values. Exactly the same? No, probably not exactly the same, but I would expect them to be at least somewhat close. And I would say to myself, the bigger the difference between my expected values and my observed values, the less likely that the null hypothesis would be true, and the more likely I would be able to reject the null hypothesis and accept the alternative hypothesis. Okay, but now the question becomes, we don't expect it to be perfectly identical, right? Because in the real world, we wouldn't expect that if we had 200, if I sample another 200 people, even if the expected values were true and there is no association, I wouldn't expect to get exactly 10 and exactly 30, exactly 40, exactly 120. I would expect to get close to that, right? So, but when we actually plot the observed values here, the bigger the difference between the expected values, in other words, imagine if instead of this being 15 and 25, this had been 39 and 1, right? Well, then you'd say to yourself, oh, wow, it's almost obvious. IV drug use, almost only the only people that are HIV positive in this study are the ones that are IV drug users, right? The other ones, there's only one person. It would be obvious to us that the null hypothesis is not true and that the alternative hypothesis is much more likely to be true, okay? But often that difference is going to be more subtle, especially because we're always limited in terms of how big a sample that we can take. Okay. The top is the expected, right? And the low, isn't that what oh, you're right. Look at that. I got caught making a mistake there. I corrected myself without realizing it there, but you're absolutely right. That was, yep, that was ye. Okay, good. Thanks for the help there. Okay, so now we're going to invent a method ourselves. Let's say that we didn't know anything about statistics. We didn't know anything else about this stuff. We're going to invent our own method for looking at how big is the difference between the expected values and the observed values. Okay, how would we, if we were going to invent that, how would we do it? Well, what we're really looking at is how different each one of these boxes are from one another, right? So maybe what I'll do is I'll just take one and subtract the other one from it. So for instance, observed value is 15 and expected value is 10. That's going to be a difference of 5. And over here, the observed value is 25. The expected value is 5, is 30. So the difference is -5. And over here, 40, let's see, 35 minus 40 is -5. And 125 minus 120 is +5. Okay, and if I add those all up, I wind up with 0. So it was a nice idea, but it didn't work out, right? And you guys might remember we had the same quandary when we were calculating variance. The difference between the mean and each individual value. When we added them all up, they cancel each other out. Negative and positive cancel each other out. Anybody remember how we resolved that so that the differences between the mean and the individual values when we calculated the variance didn't cancel each other out? Remember what we did with those numbers? Any guesses there? I never know what the lag is. I never know if in the background you're saying to yourself, I really need a sip of this cocktail more than I need to answer this question, or if we have a long lag over the internet. But I'm going to go ahead. I won't wait forever, so I'll go over and answer. Now, you guys remember what we did? We squared these numbers, right? We took the differences, x bar minus x, and we squared it. And then we added them all together. We call that the sum of squares. We're going to do almost the same thing here. So instead of 15 minus 10, the observed value minus the expected value for each box, instead of 15 minus 10, I'm going to say 5, but I'm going to square that and make it 25. And then instead of saying 25 minus 30 comes out of -5, I'm going to square that, comes out to be a plus 25 and a plus 25 and a plus 25. And when we add them all together, just like we added up the sum of squares, it came out to 100. Okay, so the bigger this number is, the bigger the difference between our expected values and our observed values. So we want this number to be big. Remember how we got this number again? We took the observed values minus the expected values, we squared them, and we added them together. Okay, added them together, that's a summation, right? A big sigma. Okay, we added them together, just added all four of those together. This formula represents exactly what we did. Observed values minus expected values for each one of these boxes and squared it. Okay, so now the only thing here is that just like when we did it sum of squares, when we added up sum of squares, because we squared it, we exaggerated the magnitude of the differences. And when we did sum of squares, the way we got around that was we took the square root of it. After we divided by n minus 1, we took the square root of it. In this case, what I'm going to do in order to get these numbers back into the range that we would expect to be working, I'm going to divide this by, well, let me think, what could I divide it? I'll divide it by the expected values. I could have used observed values, but I'll use expected values. So I'm going to take each one of them, observed minus expected, square it, and then divide by the expected value. So 25, let's see, that would be, 15 minus 10 is 5 divided by 10, right? What's that going to be equal to? That's going to be equal to 2.5. Okay, well, what about this second one? 25 minus 30 is minus 5, squared is 25, divided by the expected value, which is 30. So 25 over 30 is 5/6. Anybody know what that, any carpenters around? What is 5/6? I can't remember off the top of my head. I'll do it this way, 25. I hate computer calculators. Divided by 30 is equal to 0.833. I'm gonna just use 2 decimal places for our purposes. 0.83. Okay, 2.50, 0.83. Okay, well, what about this next one? This next one is going to be this box. I started here, 1, 2, 3. I'm going to go up here. Next, 35. Doesn't matter which order I do them in because we're going to add them all together up. Anyway, 35. 35 minus 40 is minus 5. Squared is 25 over 40 over the expected value. So what does that come out to be? 25 over 40 is 5/8. 5/8 is 0.625. 0.63, I'm going to call it. Right? That I know because in eighth of an inch, you know, when you buy a piece of lumber, you got to know that, right? 5/8 is 0.63. Am I right? 625. 625. I'll round it up 6.3. 63. Okay, what about this last one over here? 125 observed minus expected. 125 minus 120 is 5. Squared is 125 divided by 120. So 25 divided by 120. Let's get that value. Oh, here it is down here. Got a little bit of water hammer here in the background. You hear the plumbing here at Silverman is not too good, I guess. Let's see. Okay. What did I say I had? I had 120. I had 25 over 120. Okay, that's equal to 0.21. Okay, so I'm going to add these all together. Okay, so let's see. We've got 7, 10, 16, 21, carry the 1, 3.17. 3.17 is what this adds up to. Our formula here added up is equal to 3.17. We're going to call that chi-square. Chi-square is equal to the sum of all of the values for these different cells, the observed minus the expected values squared over the expected values. And that's equal, in our case, to 3.17. Well, keep in mind now, the bigger this number is, the bigger is the difference between the expected values and the table of observed values. And the bigger the difference between what we observed and what we would have expected to see had there been no association between HIV and IV drug use, the bigger the difference, the more comfortable we would be in saying that there is an association. In other words, reject the null hypothesis, no association, and accept the alternative hypothesis. Well, now, how do we decide whether this is big enough for us to reject the null hypothesis? Well, now we need, unfortunately, now that we've done this, we've invented this statistic called chi-square. Right? We did it right here in front of you. We just invented a statistic called chi-square. The only problem is we're going to need some real statisticians to go and do some advanced math and figure out what the probabilities are of getting different numbers for chi-square. And in fact, I remember this number 3.17. And in fact, they have done exactly that. Okay, what they found is that for our 2x2 table, here's chi-square is down on the bottom here, and this is the probability, and we're going to draw a distribution. Just like we had a normal distribution, we're going to draw the chi-square distribution. Well, what would we expect chi-square to be? Well, chi-square, what's the likelihood that chi-square would be 0? Well, in order for chi-square to be, and this is if the null hypothesis is true, chi-square, in order for chi-square to be 0, we would have to get lucky and get the observed values matching exactly the expected values when we took our sample of the random sample of all the people in the population, right? Well, you know, that can happen. It's not all that usual, but it can happen. But it's more likely that chi-square will be a small number, right? This could be 1, this could be 2, this could be 3, this could be 4, etc. This could be 5, right? It's more likely that chi-square is a small number down here, right? So the probability of it being exactly 0 is not too good, but probably goes up, and then it kind of peaks there, and then as chi-square gets bigger and bigger and bigger, it becomes less and less likely that chi-square, that you would get that big a difference if the null hypothesis were true. So what we want is we want to get a chi-square value that is so large that it would only happen less than 5% of the time if the null hypothesis were true. Because if it's only going to happen less than 5% of the time when the null hypothesis is true, that would mean if I reject the null hypothesis for a big number for chi-square like up here, then I'd be pretty safe because I would only be wrong less than 5% of the time. And that's usually what we set our alpha, our acceptable error for. It's usually around 5%. It could be 1%, and we'd have to be this far up this scale, right? But let's say it's 5%, we'd have to be this far up the scale. Well, what is that number? Well, fortunately, we're standing on the shoulders of giants, so we've done all the preliminary work, and we hire some really, some calculators. Have you guys seen the? Trying to think. Is it called Numbers? What's the name of the movie with the women who were the calculators for the initial astronauts for the initial NASA space program? There are a bunch of women that worked as they called them calculators. That's where the term for that machine came from, because they did all the calculations by hand on machines, adding machines, and so on and so forth. They did all the calculations. I can't think of the name of the movie. Somebody here must know the name of the movie. But at any rate, we employed a bunch of those calculators from NASA. They got laid off after the computer came in, right? So we hired them, and they did all these calculations for us, and look what they came up with. They came up with a chart, a table that represents chi-square values. And this is This is on Blackboard. You guys can look this up. Somebody must know the name of that movie. Okay, you can't hear, what's that? Yeah, no, it's not. It just escapes me at the moment. Okay. Okay, chi-square, here we go. Let's take a look at this. I hope this is the table. Is it the table? Let me close that. Oh, no, that's a little document. Okay, that's PDF. I could have used that. It's the same example. Here's the table, chi-square table.pdf. Okay, so look at this table. This table gives us the probability of exceeding the critical value is 5% for these numbers. Well, okay, let's take a look at, oh, well, hang on a second here. In order to know which one of these numbers to use for my 5% to decide whether to reject my null hypothesis for chi-square, I need to know the degrees of freedom. Anyone want to hazard a guess at how we might calculate the degrees of freedom for chi-square? N minus 1, good idea. Except n minus, is the 200? No, I don't think so. You don't see 200 on there, right? You don't see 199. For chi-square, the way we calculate degrees of freedom, it's the number of rows minus 1 times the number of columns minus 1, right? So n minus 1 is 2 minus 1 is 1, 2 minus 1 is 1, so 1 times 1 is 1. So we're dealing with a table that has 1 degree of freedom, okay? So 1 degree of freedom, our critical value is 3.841. So if I look at this chart, we need to be at 3.841. That has to be the number that we need to be at or exceed in order to have less than 5% chance of being wrong if we reject the null hypothesis. Isn't it convenient the way I just accidentally picked out exactly there, right? You wouldn't think I've done this 500 other times, right? Ad infinitum, and you're going to go on to your careers and have a great time. And in a couple of months, I'll be doing exactly the same thing again. But at any rate, look, I got lucky, and I was right there at 3.841. Anybody remember what our chi-square was calculated to be? 3.17. Okay, where is that? That is 3.17 is about over here. The probability of getting 3.17 when the null hypothesis is true might be as big as maybe 10%, right? This area could be 10%, right? That's too big for us to reject the null hypothesis. So we need our calculated chi-square value to exceed our critical value of chi-square for the degrees of freedom that we're working. Okay. What did we need? If I had said I wanted to be, alpha was alpha is equal to 0.01 or less than 0.01, what would chi-square be a bigger number or a smaller number? It'd have to be further out, right? So it would have to be a smaller number. I mean, a bigger number. Okay, so let's take a look at that. So in other words, chi-square would have had to be out here somewhere, right? So only 1% chance of it occurring if the null hypothesis were true. Okay, let's see what that looks like in our table. Okay, and so for 1%, chi-square would have to be 6.635. Right? Have to be 6.6 in order for us to reject the null hypothesis. But usually we're happy at 5%. That's coming from, I'm looking at the graph, and I'm saying to myself, at 3.17, it looks to me like about 10% is left, right? So we will need to be out here at 3.84. We need a value like 4 or 4.5. So there's less than 5% chance that we would get that big a chi-square value if the null hypothesis were true. In other words, the expected values are equal to the observed values. So
now we have it's critical more than what we calculated.
Right. So that means we didn't get a big enough chi-square. The difference, remember, the chi-square we calculated represents how big the difference is between the expected and the observed values are. So we didn't get a big enough difference between the observed values and the expected values. So we can't say with less than 5% chance of being wrong that they're not different, that they're different, right? So we need to exceed the critical value of chi-square in order to be at least certain enough that we could say with at least this level of confidence, less than 5% chance of being wrong, that the null hypothesis is not true, and reject it and accept the alternative. Okay, so just like the t-test, we did the same thing. We needed the t-value we calculated to be bigger than t-critical. When we use SPSS, we actually get a p-value. The probability that we would get that extreme a value if the null hypothesis were true. And you can just look to see if it's less than 5% chance that the null hypothesis is true, and you can reject the null hypothesis. With chi-square, if we're not using SPSS, just like with the t-test, if we're not using SPSS to calculate the p-value, well, then we can instead, use the table and look to see what the critical value that we need to exceed is. We did the same thing with the t-test, right? We calculated t-test, checked the table with the t-score to see if we exceeded the critical value. But then in real life, we would probably just use SPSS to do that for us.
So the answer right now, what we figure out is that HIV and IV drugs, they're not related.
We didn't prove that. We failed to prove that, right? Because we
rejected their equal.
No, we didn't reject. We failed to reject. We failed to reject the null hypothesis that they're equal. Why did we fail to reject? Because our chi-square number wasn't big enough. The difference between the between the observed values and the expected values didn't produce a big enough number for us to be sure that they were different, right? So we could have gotten that result by chance, like in other words, 15 instead of 10 and 25 instead of 30. We could have gotten that just by chance, even with the null hypothesis being true, that big a difference. But now if we went back and did it again with a bigger difference between the expected values and the null hypothesis, we might actually have a shot at proving it, maybe a bigger sample or something like that. Okay, so you guys online, do you agree with me on this? Are you comfortable with this? I want to do one more of these, okay? Except this time I'm gonna turn things around a little bit. I'm gonna leave this out of here. We're gonna want to refer to it. I think I got a data set here we can use. Let's see. Stenosis. I wonder if I have this in a couple of forms. Let's see. I got paper versions there. Let's use that. Paper versus air came up a different thing here. Oh, maybe because I'm sure. Oh, okay. Okay, so we're going to take a different. This is a more realistic description of what the data might look like when you do a survey. Okay, so I'm going to say that we sampled 98 people. We went out and did a survey of 98 people. That we've noticed that a lot of people have been getting the flu in our office, and we're very careful about sanitizing all the different surfaces and nobody sharing stuff and so on and so forth. But now, we think maybe that it's got something to do with those hot air blowers they use in bathrooms. You ever wonder about that? Go take your dirty hands, you wash them, and you stick your hands under there, and you blow air over them, and it's blowing everywhere, like a hurricane, like a tornado at 300 miles an hour. It's blasting every particle, every germ off your hand all over the room, right? You ever wonder whether or not that was safer? They supposedly, it's nice because you don't have to touch anything, but on the other hand, it's blowing it's atomizing whatever's on your hands into the air. You can breathe it, and somebody else is using it ahead of you, and so on and so forth. So let's say we wanted to do a study, and we sampled in the office. A lot of people getting sick. How many people were getting sick? Out of 98 people we surveyed, 29 of them had gotten the flu, right? So we asked them. Let's see, but that means out of 29 got the flu. That would mean that let's see, 69 did not get the flu, right? Let me get that out there. Okay, 69 did not get the flu. Okay, so we surveyed these people and we asked them, which one do you use when you go into the toilet? Do you use paper, or do you use that ridiculous blower, which is like, you need earmuffs to use the thing? Like, that's the other thing. I wonder if it's you need hearing protection when you use those things. So we asked them, which do you use, right? Turns out that of 46 people said we use the paper, and 52 people said we use the hot air. Okay, and let me think about this here. Let's see, those 46 people, when we break it down further, turns out 19 of them had the flu, 27 didn't get the flu that year. Adding up to 46, what about the 52 that used the hot air? Well, 10 of them used hot air, and 42 used, 10 of them got sick that used the hot air, and 42 didn't get sick that used hot air. Right? Remember, the manufacturer's claim for this is that those hot air things, they're more sanitary than the paper is, right? For a number of reasons. You got to touch the can when you throw them away and whatever else. And you don't clean as well, maybe. I don't know. You don't dry as well. Okay, so, but we're looking for this. So what's our null hypothesis? What do you think would be a good null hypothesis? Null means they're the same. Null is there's no association. No association between the drying method you use and getting sick. Oops. No association between the drying method and getting sick. An alternative hypothesis, there is an association between paper or hot air and illness, right? So in null hypothesis, there's no association. So in our null hypothesis, we would expect our observed values to match the expected values that we would get. Oh, now we got a little bit of a problem here. We did that. This time, I didn't give you the expected value. We're going to have to figure out the expected values, right? How might we figure out what the expected values are? Well, first of all, we know that there were 46 people. Yep, click into that. My keyboard, my trackpad's not being cooperative. There were 46 people who used paper. There are, okay, there are 52 people who used hot air. Not 52. For a total of 98. Okay. And there were 29 people who got sick. We can't change that. That's got to stay the same, right? 69 people, I mean, that's just a fact. That's what happened. But now, what would we expect to be the distribution in here? Well, first of all, what's the prevalence for illness in this population? What percentage of the people got sick in this population? It's going to be 29 out of 98. So the prevalence, oops, I'll put it over here, equals 29, 98, okay, a little less than 0.3. That's our prevalence. Okay, so now that's our prevalence. So now, out of these 46 people who use paper and 52 people who used hot air, what percentage would we expect of these 42 people to get sick in this population? We'd expect to get it at whatever rate the population gets sick, right? If there's no, doesn't matter which one you use, we would expect them to get sick at the same rate, which is the prevalence for the population, 29% of the time they get sick. Okay, so what's 29% of 46? Okay, 46 times 0.296, 13.6. How many people actually got sick? Well, 19. That's quite a big difference between our observed values and expected values. Well, what about this group here? What about hot air? What percentage of the people that use hot air would we expect to get sick? 29%. Because if there's no association, if it makes no difference whether you use paper or hot air, they should get sick at the same rate, right? So this is going to be 52 times 29.5%. Okay. Notice I'm not rounding off until the very end, right? Because if you round off, you're going to multiply by things, and when you multiply them, if the error is 1/10 of 1%, you multiply by 30. Now all of a sudden the error is 3. Right? It really blows up the error. Okay, so now what about this? What's this got to be? Well, this is going to be equal to 46 minus 13.6, right? Because it's got to add up to 46. And this is going to be equal to 52 minus 15.38. And that comes out to be 36. And you'll notice that these two add up to 69 and 29. So it balances out. So what do we have here? We have 19, 27, 13, and 32. Wow. Look at the differences here, right? Differences are pretty interesting here, right? They look a little bit bigger than the differences we saw before. Maybe. I don't know. We don't know yet, do we? Right? So now I say to myself, okay, so now in order to test my null hypothesis, I'm going to use chi-square. And how does chi-square work again? Chi-square, and I'm going to do it down here for each box. Chi-square is equal to the observed values minus the expected values. Right, I'm going to put them in parentheses. And I'm going to use that little caret thing, squared, divided by, what is it divided by? The expected values, right? So that first box is going to be 2.131. So the second one is going to be, let's put this equals, it's going to be the observed value minus the expected value. And I'm going to square that. And I'm going to use a little shift 6, a little caret, squared, divided by the expected value, which is 15.38. Well, that's 1.688. Equals, I'm going to do this again now. The observed value is 27, minus the expected value is 32.38. And I'm going to square that. Divided by the expected value. And then finally, I'm going to do it for the last one. The equals the observed value minus the expected value divided by the expected value. Okay, so my chi-square is equal to the sum of all these, right? So I'm going to do this right here. Equals the sum of these four numbers. Oops. Equals 5.06. That's what chi-square is equal to. You can type that, or you can use the description. Oops. I know what it wants. It wants a space in front of that equal sign. If I don't put a space in front of that equal sign, it figures I'm going to calculate something. Okay. So it's 5.06. How many degrees of freedom do I have in these tables? 1 degree of freedom, right? And the rows minus 1 times the columns minus 1, 2 minus 1, 2 minus 1, 1 times 1 is 1, right? So 1 degree of freedom. Do you happen to remember what the critical value was for chi-square? Yep. Critical was equal to, come on, let me click in here. Wait, the computer really don't want me to do this. Equals 3.84. 3.84. That's our critical value of chi-square. Have we exceeded our critical value of chi-square? Yeah, the differences are so big in these two tables that I got 5 instead of 3.84. So there's a big difference. There's a bigger difference between these tables than there was in the first set that we did before. Okay? So that means we can reject our null hypothesis and accept our alternative hypothesis with less than a 5% chance of being wrong. Right? That's not so difficult, right? It's as long as you keep it methodical and you're careful with your calculations, it shouldn't be that hard to beat. The only thing that's a little tricky is figuring out, in this case, you had the observed values, so you had to figure out what the expected values were. So if you use Excel, you have to calculate the expected values in order to complete this calculation. When we get into SPSS, we're not going to have to do that. SPSS will do that for us. Matter of fact, guess what? We have another copy of this table in SPSS form. Okay, and again, this is on Blackboard. If you want to work along with me, paper versus error. I'm going to open that up. I double-clicked it. I'm going to wait for a little while because if I get impatient, I wind up opening SPSS 5 times. Right. One times one. Multiply 1 times 1.
Oh, they're not applied.
Right. Okay. My user license is going to expire in 24 days. We have about 21 days left of this class. I'm just going to make it. Okay. I don't know how many of you guys are in the same shape. Okay, so let's see what we have here. We have ill, not ill, paper, and so on and so on. We have 2 variables, hand dryer and illness. And both of those are nominal variables. I'm going to click on the variable view so you can see this. Type of hand dryer, developed illness. You can see the label that we use. We gave it a label, so it'll be a little bit more descriptive. Since they're both nominal, we can give them values. So 1 equals paper, 2 equals hot air, and 1 equals ill, and 2 did not get ill. Okay. And if we go back here, here's the data. And if I go up to view and turn off the value labels, you can actually see the numbers, right? Each person, each subject is described here. This person used hot air and got ill. I think, I don't remember the numbers, tell you the truth, but you get the idea. This person used paper and did not get ill, or something like that, right? So you can figure that out for yourself. Okay, so I'm going to leave this turned on. It's nicer to be able to see it rather than seeing those numbers. And I am going to step through what we just did now. I'm going to say analyze. Okay, so are we comparing means here? No, we're not. This is not numerical variables. We can't compare means, right? Okay, let's see what we can find here under descriptive variables. Under descriptive statistics, we see something called crosstabs, right? That's the way we lay out the data. I'm going to click on that. Okay, and it gives me a number of options here. First of all, it's waiting for me to tell it what goes into the rows and what goes into the columns. In general, we're almost always going to put the exposure in the rows and the outcome in the columns. So the exposure is the kind of hand dryer that you use. And the outcome is whether or not you develop respiratory illness. Okay, good. Okay, so we got that done. And let's look into these boxes here. Statistics. Okay, chi-square. Look, nothing's checked off here. You want to know something? I don't want to get ahead of the game. I'm going to leave that unchecked. I'm going to go into cells. And right now, the only thing that's checked off is observed. Okay, and it says also round cell counts. That's okay. I'll leave it. Even though it rounds them, it really hides the real values in the background. So it's not rounding it in the sense that you would and losing that information. It just makes it more convenient to look at. I'm going to click OK. The only thing I answered to do so far is to show me the observed values. And here we go. It took that data and laid it out just the way we did with our manually generated chart. Out of 46 people who used paper, 19 of them became ill. Out of 52 who used hot air, 10 of them became ill. And there were 98 people, and 29 to 98, and we could look up the prevalence and so on and so forth if we wanted to. Right? But right now, I'm okay with that. Okay, well, gee, what about observed value, expected values? I got my chart says observed values. What about expected values? I'm going to go back up here to analyze, descriptive statistics, crosstabs. And now I'm going to go back into cells. And I'm going to say, show me the expected values. Show me the money. Show me, you remember that movie? What was that? Jerry Maguire, right? Show me the money. You don't watch movies? What's that? Hidden Figures, that's it. That's it, exactly right, Hidden Figures. There's another movie, Jerry Maguire, where one of the actors keeps, it's a football player, and Jerry Maguire plays his agent and keeps telling the agent, show me the money. So let's click expected values, say, okay, show me the expected values, in this case, not the money, right? And let's see what we have here. Well, look, it's showing me, it looks just like we did before, 13.6, 32, 15.4. These should look pretty familiar to us, because that's just what we had calculated by taking the overall prevalence and multiplying the number of people in that row by the overall prevalence to get 46 times 29% to get 13.6 and so on and so forth. So that did exactly the same thing. I got a no over here from someone. A no to what? About what? Oh, the movie. Okay. Okay. So these are expected values. Now, SPSS doesn't bother to display them in separate tables. It just puts them into separate rows. So you actually see the two cells. This would be the top left in the observed values and the top left in the expected values. Now, notice that whenever we talk about observed values, you can tell which of the observed values and which of the expected values immediately. How could you tell? They're integers, right? Because observed values, you're not going to get half a person, right? When you ask that person, did you get sick? Well, I got half sick. I got half, didn't get half sick, You're not going to get that, right? They either get sick or they didn't get sick. So it's always going to be a whole number. The expected values almost always will be fractional numbers. Okay, so you can tell them apart easily. So I'm going to go back up here to analyze, descriptive statistics, crosstabs. Okay, except this time I'm going to go into statistics. And I'm going to ask SPSS to calculate the chi-square value for me. And I'm going to click OK. It's going to do all the calculations it did before because it's still part of that. And let's look down here. This is called, by the way, this is called the Pearson's chi-square. Okay, and if we look at that, what did we get before? We got a 5.7, I think. I hope. 5.06. I think maybe possibly that the data sets are a little bit different because I tinker with them occasionally. Because SPS is just calculated as 5.7. Okay, but don't worry about that because I think the data set in the SAV file and the data set in the Excel file might be a tiny bit different. Right, that's why we got that. 1 degree of freedom. Okay. Now notice that alone, that chi-square alone with 1 degree of freedom tells us we can reject the null hypothesis because it's bigger than the critical value for 1 degree of freedom. But if we need more evidence, here's the probability, exact probability that we would get this big a difference between the observed values and the expected values if the null hypothesis was true. We would only get that outcome 1.7% of the time, less than 2% of the time. So if we would expect to have only 2% chance of getting this outcome if we reject the null hypothesis, and it turns out to be true, it would only happen 2% of the time, we're willing to take that chance as long as it's less than 5% chance. So if this p-value or significance is less than 0.05, we reject the null hypothesis. Just like if this value for chi-square is more than 3.884, we would reject the null hypothesis. Both of these are evidence that go along with each other to reject the null hypothesis. Okay, see this thing over here called continuity correction, right? There's a different version of this, of the Pearson's chi-square. What do you think that might have something to do with? Continuity. Well, real numerical scales are continuous, right? Like our expected values, 37.934. 42.7926. It's a continuous scale. But when I did the observed values, was that continuous? No, it wasn't. There were integers, right? So in other words, you couldn't get 32. So when you compare the observed values to the expected values, there's a little bit of a problem. The observed values are constrained. They can only be integers. So there's something called the continuity correction. And what you do is you take, this introduces a little bit of extra error because the observed values can only be whole numbers. So they kind of distort the exact probabilities. So what we wind up doing is, in order to correct for that little bit of extra error that we might be introducing there, the continuity correction says, take the sum of the observed values minus the expected values minus 0.05. Half point is 0.5, right? Which is half, right? In other words, half a person, one person, 32 people, 34, 33 people, 32 and a half people. Observed values minus the expected values minus 0.05. Square that and put it over the expected values. And do that for each cell. With that extra 0.5 being subtracted, that makes this number smaller. Each one, 4 times in each one of the boxes makes it a little tiny bit smaller, which winds up giving you a chi-square, a continuity corrected chi-square, which is a little bit smaller than the Pearson's chi-square. And where would this be important to us? This would be important to us when we have a very small sample. For instance, when one of the boxes has 5 or fewer people in it. So in general, for our purposes, we can ignore that. I'm not going to give you an example that'll trip you up on that, right? But that's what the continuity correction is for. Don't worry about it. I'm almost sorry I even brought it up at this stage, right? Don't worry about it at all, right? But really, what I really want you to remember is how we calculated this. Okay, pretty interesting, right? Okay, so that is Pearson's chi-square and continuity correction, but we're going to be dealing with Pearson's chi-square for the most part. Okay, so now, and if you look down here, 0 cells have expected count less than 5. The minimum expected count is 0.5. That's one of our general rules, and this is, okay, that's all we need for right now. Okay, so I'm going to go back and take another look at something. Okay. Okay, so what will I use as an example here? I'm going to go back to my HIV status. These are my observed values. HIV positive, HIV negative, and this is, oh, wait a second. What am I doing? IV drug use positive, IV drug use negative, HIV status positive, or HIV status negative. Okay, and so this time I'm going to say it's 200 people and 40, and I'm going to say, let's say 10, and I'm going to make this a little bit different. I'm going to call this 50, 10 and 40. This will be 150, changing things just a little bit here. Okay, this is going to be, and this is going to be, no, I'm going to do this the opposite way. I'm going to make this 40, this 10, and 50, 150. I'm going to put 100 people into each one of these two groups. Okay, so 40, this is going to be 60 people. This is 10, this is going to be 90 people. Okay, so if you're an IV drug user, right? We had 100 people out of these 200 that were IV drug users. 40 of them were HIV positive. And among the group that was not an IV drug user, we had 100 people who were non-IV drug users, and only 10 out of 100 were HIV positive. Very interesting. So let me ask you something. If you're an IV drug user, what's your risk, or what's the probability that you are going to be HIV positive? What's the risk of your being positive? The risk is 40 out of 100, right? Your risk is 40%. How about if you're not an IV drug user? What's your risk? Your risk is 10 out of 100, or a 10% chance that you are HIV positive. Now, I'm going to take a ratio here now. And I'm going to say the ratio, the risk of 40% over the risk for non-IV drug users is 10%. I'm going to put one over the other, and I'm going to call that the risk ratio. That's going to be 0.40, whoops, 0.40 over 0.10, and that's equal to 4. What does that tell us? That tells us you're 4 times as likely to be HIV positive if you're an IV drug user versus if you're not an IV drug user. Boy, that's very clear, isn't it? I mean, that's something you could put in the papers and it would explain it to non-statisticians. We see that all the time. Your risk of getting lung cancer if you're a smoker is 5 times that of if you're not a smoker. Your risk of getting lung cancer is 7 times greater if you've been exposed to occupational exposure to asbestos, right? And so on and so forth. We can understand that, and we can understand synergy, for instance, from that. If you're a smoker and it's exposed to asbestos, your risk is 35 times a person that's not a smoker and not exposed to asbestos, right? We can wrap our heads around that. That's called relative risk. Well, let me ask you something. What would the relative risk be if there were no difference between being an IV drug user and not being an IV drug user? If there were no difference in the rate at which these people got HIV, it'd be 1, right? In other words, the risk on top. So, like, in other words, if this were out of 100, if this were 25 and 25, 25 out of 100 is 0.25, 25 out of 100 is 0.25. The relative risk, the null hypothesis for the relative risk is that it's equal to 1. If the risk for people who have the exposure over the risk to people who don't have the exposure is equal to 1, it means there's no difference in risk, right? So our null hypothesis is our relative risk is equal to 1. Our alternative hypothesis is our relative risk is not equal to 1. Oh, great. Okay. So is 4 a big enough difference for me to be able to reject the null hypothesis? What do we need to know about that number in order to know whether or not we can reject the null hypothesis? And think about this. It's a concept that we've already learned. We've used it with proportions, with numerical variables, confidence interval, right? We need to know the confidence interval for this result. So in other words, I can tell you the relative risk is equal to 4, but that doesn't help you. I also have to tell you that the 95% confidence interval is 2.5 to, let's see, 5.5, right? So we're 95% sure the true relative risk for the population is between 2.5 and 5.5. Well, since we're 95% sure that the true relative risk is between these two numbers, are we also 95% sure that it's not equal to 1? Yeah, if we're 95% sure it's between these two numbers, we're pretty sure it's not 1, right? Because that's outside of the confidence interval. Well, now what if I had told you that the relative risk came out to be 4, but our confidence interval was 0.8 to 8.6? Can you still say that the relative risk is different than 1 with 95% certainty? No, you can't, because it could be 1. It's inside the confidence interval, right? We can't be 95% sure. So we need to know the confidence interval. We're not going to go into calculating the confidence interval. This is calculating the relative risk is easy, right? Just look what we did. We just figured it out. No big deal. Calculating the confidence interval is a little bit more difficult because we're dealing with proportions. We've got to calculate confidence intervals with proportions and so on and so forth. At small numbers, smaller samples, and so on. We're going to leave that to SPSS. But you get the concept of what the relative risk is. And it's a nice concept because it's easy to wrap your head around. Okay, so now I'm going to change it up a little bit now. And the reason why I'm going to change it up is not because I want to, but because I have to. Because in most cases, statisticians don't really use relative risk. They use something else. I'm going to take the same numbers we were working with before. Okay, this is HIV plus and minus, and this is IV drug use plus IV drug use minus, and 100 people here, and 100 people here, and 50 people, and 150 people. And I'm going to say, what was this again? This was 40, and this was 10, and this is 60, and this is 90. Okay, so now remember relative risk. 40 over 100 is 40%. 10 over 100 is 10%. 40% over 10% is 4. Right? I'm going to do something else. I'm going to do something differently this time. I'm going to calculate odds. Odds are different. Have you ever gone to the racetrack? Put a bet down. You went once. Did you win or lose? That's bad. That's dangerous. Winning the first time. A lot of people, that's very dangerous. You want to lose the first time, because if you lose the first time, you won't get the fever. Oh, it wasn't fun. Okay. 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 So at the racetrack, when they tell you a horse is 4 to 1, the odds are 4 to 1. That doesn't mean it's 4 times as likely to lose as win. Right? 4 to 1 means it's going to pay off 4 times as much. But that doesn't mean it's 4 times as likely to win. What that means is that if the horse ran 5 times, you'd expect it to lose 4 and wins once. So a horse that's the favorite might be 2 to 1. It might, for every 3 times for every 3 times it runs, it may win once, right? So the total outcomes are 3, right? So really, it's a little bit different than calculating risk, right? Because really, if I look up here to our table, right? What are the odds that someone who is an IV drug user has AIDS? Well, out of 100 people, 40 times they'll have it, 60 times they won't have it. So the odds for IV drug users, for IV drug user positive, is 40 over 60, or 0.667. See the difference here? The risk was 40 over 100. Now the odds are 40 over 60. So what are the odds for non-IV drug users? The odds are 10 over 90. right? Which is equal to, I got to use my calculator for that. That I definitely don't know off the top of my head. 1 divided by 9 is 0.11111 equals 0.1111. That's the odds for non-IV drug users. So what do you think I'm going to do next with these two numbers? I'm going to find the ratio, the odds ratio. Okay, and the odds ratio is 0.667 over 0.111. What does that come out to be? Yeah, 0.667 divided by 0.111. And that comes out to be 6.6. I'm going to call it roughly 6. Remember what the relative risk was? Relative risk was 4, right? The odds ratio comes out to be 6. In some cases, the odds ratio kind of exaggerates the difference, which is kind of good. Again, makes it a little bit more obvious, a little harder to wrap your head around, right? But more studies tend to use the odds ratio than the relative risk. But again, if the odds were the same, if this were instead, if the 100 people up here and 100 people down here, if this were 25, 25, 75, and 75, it would be 25 over 75 would be 0.33. 25 over 75 is 0.33. The odds ratio would be equal to 1. So the odds ratio equals 1 is our null hypothesis. There's no difference in the odds for either group getting HIV, right? So our null hypothesis is the odds ratio is equal to 1. Our alternative hypothesis is that the odds ratio is not equal to 1. Okay, and what do I need to know besides that number 6 in order to be able to judge, or can I reject the null hypothesis of the odds ratio being equal to 1? I need not only that the odds ratio is equal to 6, but I also need the 95% confidence interval for the odds ratio. And let's say that that is 3 to 9, right? 3 to 9. Can I reject the null hypothesis? Right? What? Well, no, 3. Yeah. Right. So the odds ratio we calculated was 6, but the confidence interval for that is 3 to 9. So is 1 inside that? No. So we can reject the null hypothesis and accept the alternative hypothesis. We just discovered 3 different tests for telling us the same thing: chi-square, relative risk, and odds ratio. They all work together. Theoretically, whenever one allows you to reject the null hypothesis, they'll all allow you to reject the null hypothesis. Some studies you'll see them use chi-square, right? Some studies you'll see them use odds ratio. Can you think of a reason why you would not be able to use odds ratio, but you would be able to use relative risk? This is a little bit of a curveball. What's that? No, not sample size. You got kind of the right idea, though. You're going the right direction. What if instead of a 2x2 table, it's a 3x3 table, right? Like no smoke, never smoked, never smoked. I can't draw on that. Never smoked, ex-smoker, and smokes currently. And let's say no lung disease, moderate lung disease, serious lung disease, right? That's a 3x3 table. You could have that, right? Could be 25 people in here, 15 people. You could do chi-square because you could create an expected values table from this, just like you could for a 2x2 table, and you could calculate your chi-square value. The only difference is that now instead of having 4 numbers you add together, you have 9 numbers you add together for each of the boxes. And instead of 1 degree of freedom, now you have 3 minus 1 is 2. 3 minus 1 is 2. You have 4 degrees of freedom. So your critical value of chi-square now is a much bigger number, right? So you can do that. However, you can't calculate odds ratio, because what do you need to do odds ratio? You need a 2x2 table. You can't do it for a 3x3 table, right? Because what number would you get? Which two numbers would you use here? This one and this one, this, you can't do it. SPSS will tell you that you can't do it for you can only do it for a 2x2 table. Okay, so that's a little bit of a curveball there, but just keep that in mind when you're doing this. SPSS will keep you from making that mistake. If you try to do it for something bigger than a 2x2 table, it'll tell you, hey, you can't do that against the rules. Or I don't know how to do that, be more likely. You can get around that. There's some tricks to get around that. We'll worry about that next week, after the test and after we do the initial homework. There's some ways to get around it. Okay. So I think that this is an excellent time for a break. Okay, we'll take 10 minutes, and I'll get my voice back, and I'm gonna do another example with SPSS in calculating chi-square, relative risk, and odds ratio all at the same time from the same data. Okay? Okay, guys, take a break, 10 minutes, we'll be right back.
This conference will now be recorded.
Okay, we're back. And there was a question, could you explain again how to get degrees of freedom for chi-square? Was it degrees of the rows -1 plus columns -1? Close, but no cigar. I must have misstated, because you got the same impression. I might have misstated it at some point. It's rows -1 times columns -1. Okay, so if we have a 2x2 table, let me turn on recording again. Oh, we are recording. If you have a 2x2 table, it's 2 minus 1 is 1 times 2 minus 1 is 1. 1 times 1 is 1. Don't add them together, multiply them together. So we had that 3x3 table that I was describing just before we took the break. That would be 3 minus 1 is 2 times 3 minus 1 is 2. 2 times 2 would be 4 degrees of freedom. Okay, so you multiply those two. But okay, good. All right, glad we got that straightened out. Okay, so now I'm gonna look at doing this strictly using SPSS. Okay, so I got a new data set. And first of all, I just want to show you what it looks like in Excel, even though I'm not going to go through the exercise in Excel. It's called stenosis and smoking. This is the SAV version of it. It's on Blackboard. And this is the chi-square Excel stenosis. This is the version of it that's in Excel. Okay, now my version, I filled in these three numbers at the bottom. I think in the version on Blackboard, this says 500 for some reason. I might have been tinkering with it as I was talking during a previous lecture or something like that. But you can see it adds up to 215, and this adds up to 98, this adds up to 117. So this would be how it might look, the table might look after you've completed collecting your data from a random sample of 215 people in this population. Stenosis is coronary artery disease. It's narrowing. I think it's narrowing of the arteries. At least that's the way stenosis is used with bones and stuff like that. But this is narrowing of the arteries, and this is the effect of smoking. So a null hypothesis would be that there's no association between smoking and stenosis, coronary artery disease. And our alternative hypothesis would be, yes, there is an association between the two of them. So we're starting with the assumption that there is an association. So we would then use this information to create a expected values table. And we'd start off by figuring out what the prevalence is in this population of stenosis. Obviously, this is a elderly population with a high rate of heart disease and so on and so forth. So 98 over 215. So the prevalence is more than 40% in this population. And then what we would expect that of the 94 people who smoke, right, we would expect 40-something% of them to be within this box, yes, for stenosis. And among the ones that didn't smoke, we would expect 40% of this 121, or about 30 people to be in this box, yes, for stenosis. right? Only 40% of 121. Okay, and in fact, we would then compare our expected values to our observed values to see if the differences were large enough and generate a large enough chi-square on a 2 by 2 table, 1 degree of freedom, to reject the null hypothesis that there's no association between smoking status and stenosis. Okay, so we're going to do this in SPSS, and here is a table. Here's the same data in SPSS. It's organized, so we have 3 variables in this particular data set. Smoking status, yes or no. Disease status, yes or no. And gender, male or female. So we have 3 categorical variables that we're working with here. Okay, so I am going to go ahead and I'm going to start this analysis. We're really at this point just interested in smoking status and disease, coronary stenosis. So analyze, descriptive statistics. I'm going to make my table up first. Crosstabs. I'm going to take advantage of being able to do this in SPSS in a step-by-step manner. You could literally do all of this at once. So in the rows, I'm going to put my exposure, which is smoking status. And in the columns, I'm going to put my outcome, which is disease, or in other words, the prevalence of aortic stenosis, the presence of aortic stenosis. In cells, I'm going to tell it to show me the observed values, just to see if it looks the same as the one I saw in Excel. And if I look at it here, boy, it does look exactly the same as the table that I saw in Excel just a moment ago. Okay, so now I'm going to do something interesting. I'm going to go over here to Analyze, Descriptive Statistics, Crosstabs. Kind of hidden there, isn't it? And I'm going to go into Cells, and I'm going to tell it, show me the expected values. Okay, and it will calculate the prevalence, apply that prevalence, and give you your second table, 42.8, 51.2, 55.2, and 65.8, which is your expected values. And if you were going to use this now to calculate your chi-square value, you take your observed 54 minus 42.8, square it, divide it by 42.8, your expected values, and then repeat that in each one of the 3 other pairs of boxes, expected and observed values, to calculate your chi-square value. You don't need to do that because SPSS is going to do it for you. So at this point, knowing the expected count really doesn't help me any because SPSS knows it. It's going to use it to calculate it. So I'm going to get rid of it. I don't really need to look at it anymore. But what I will do is I'm going to ask it to show me the percentages by rows. Okay, let's see how that helps me. Okay, so now I'm going to calculate my table again. And here's my table again, my expected values, 54, 40, 44, and 37. And look at this. Among the people that smoked, 57.4% had stenosis. Among the people who didn't smoke, 36.4% had stenosis. Well, what is that? What is that percentages by rows? Well, that's 54 over 94 and 44 over 121 to get that 36 and that 57%. That's our risk. So our relative risk would be 57.4% over 36.4%, or roughly, it looks like roughly about 1.5. So the risk ratio is about 1.5. It's 57% over 36%, 0.57 over 0.36 is about 1.5. So people who smoke are 50% more likely to develop stenosis, according to our calculations. In order to know whether I can reject the null hypothesis that the relative risk is not equal to 1, a null hypothesis relative risk is equal to 1, alternative hypothesis relative risk is not equal to 1. In order to reject the idea that relative risk is equal to 1, in other words, there's no difference in risk, I need to see the confidence interval. And we didn't calculate it here yet, but it's going to come up soon. So I'm going to go back now, and I'm going to say Analyze, Descriptive Statistics, Crosstabs, except this time I'm going to go into Statistics. I'm going to ask SPSS to calculate the chi-square value for me. I'll click OK, and click OK, and now it's calculated the chi-square value for me. Well, we have more than, the expected value has more than 5 people in it. It's a decent sized sample. I'm going to ignore the continuity correction, just use Pearson's chi-square. How many degrees of freedom here by the 2 by 2 table? 1 degree of freedom. And that value, 9.48, 1 degree of freedom. If I were to look at my chi-square table, you might remember that the critical value of chi-square for 1 degree of freedom is 3.84. We've exceeded the critical value, which means that these tables are so different, we can say, we can reject the null hypothesis that there's no association between smoking and stenosis, and accept the alternative that there is an association, right? So, in fact, we could actually go over here and see the strength of this association. The probability we would get that big a difference between these two tables, expected and observed tables, and this big a chi-square value is less than 1%. It's actually 0.2% of 1%. It's well below 5% chance that we're willing to risk in rejecting the null hypothesis. So the fact that this number is so big and the fact that this is less than 0.05 allows me to reject the null hypothesis using the chi-square calculation, okay, which is really the difference between the null hypothesis and the, which is the difference between the observed values table and the expected values table. Okay, so now, what about odds ratio and relative risk? What happened to them? Well, I'm going to go back to analyze. I'm going to go to descriptive statistics crosstabs. Okay, and I'm going to go into here to statistics. I'm going to check off one more thing here. I'm going to check off risk. Okay, and I'm going to click continue. When I check off risk, it tells SPSS to run another series of calculations, which include risk and odds ratio. So here is our chi-square table. It's reproduced once again, as well as our observed value tables and our percentages by rows. And let's take a look down here. What do we see? We see that our odds ratio for smoking status, yes or no, is equal to 2.363. Well, how did we get that? That's 54 over 40 divided by 44 over 77. And that turns out to be 2.363. So our null hypothesis for odds ratio is that the odds ratio is equal to 1. There's no difference in the odds for having stenosis among smokers and among non-smokers. Odds ratio equal 1. Or alternative hypothesis that there is a difference. The odds ratio is not equal to 1. So we can see here we calculated it's being pretty different than 1, 2.363, but that's not enough. We have to know what the confidence interval for the odds ratio is to make sure that 1 is outside of the confidence interval. We're more than 95% sure that it's not 1. So what's our confidence interval? In SPSS, unlike in our manual calculations, SPSS has actually calculated confidence interval for us. So the confidence interval for the odds ratio is 1.361 to 4.102. So is 1 within our confidence interval? No, it's outside of confidence interval. So therefore, we can reject the null hypothesis that the odds ratio is equal to 1 and accept the alternative hypothesis that it's not equal to 1. Basically the same conclusion as rejecting the null hypothesis of association for our chi-square test. What about relative risk? Remember relative risk, right? We don't, in studies, they don't use that quite as much, but it's kind of even a little bit more descriptive in my opinion, right? Remember I said it was about 1.5? Well, here is relative risk right down here. They call it for cohort presence of aortic stenosis equals yes. That's their description of what is basically relative risk. And it's 1.580. And again, what's our test here? Our relative risk is equal to 1. Our alternative hypothesis, our relative risk is not equal to 1. So we got to make sure that our confidence interval for relative risk does not contain the value 1. And 1.179 to 2.118, 1 is outside of that confidence interval. So we're 95% sure we can reject the null hypothesis. So we have 4 different ways we've rejected the null hypothesis here, right? By having a chi-square value that exceeds the critical value, by having a significance for the chi-square value that is less than 0.05, by having an odds ratio that's different than 1, and with a confidence interval that excludes 1, and having a relative risk that's different than 1, and and a relative risk that excludes the number 1. Okay, so a lot of ways to skin a cat here, right? But keep in mind, chi-square you'll be able to do for any number of rows and columns, but relative risk and odds ratio will only work for in SPSS for a 2x2 table. We'll deal with, like, situations where we might run into problems with that later on. But for now, I'm going to leave that as is. Okay, so I want to do one more thing. I'm going to leave you with something to watch on your own, and that is on Blackboard. Let me just open it up so you can see it. On Blackboard, there is a lecture, a recorded lecture. Okay, PowerPoint. Like by this point, you know that I'm not a big fan of PowerPoints. But, however, there is material in there that you should be exposed to. Some more details about assumptions in these statistical tests, and when they can be applied, and so on and so forth. So you should watch it. And you never know, there might actually be a multiple choice question here or there that comes from the PowerPoint. Okay, and if you look over here, let's see, where are we? Can you see that's session 12? Am I in the right spot here? No, I'm not in the right spot. Here we go. Session 12, that's us. And here you go. And here's the lecture. There might be some other stuff that's extraneous here. There's a long one left. Okay, but you'll see the lecture, and you have the PowerPoint itself here if you want to just spin through the PowerPoint. Instead, I think I've covered about 90% of what's in this lecture here, but there might be a little odds or end that you should pick up. And if you don't have the time or the inclination to watch the entire lecture, especially with PowerPoint, it can get a little tedious. You can open up the PowerPoint or the PDF of the PowerPoint and spin through the slides. So if you see anything that I forgot to bring up now, it will help you out. Also, you'll see a lot of the notation in a more formal layout than perhaps I used tonight. Okay, but what I want to tell you about is I'm going to go back here and I'm going to take one more data set here. Actually, maybe I won't take a new data set. I'm going to stick with the old data set. By the way, that was the end. And I'm going to ask you to do a calculation on your own. I want to know if there's an association between stenosis and gender. So look, we have another variable here, gender, instead of smoking status. So I want you to tell me, do the statistical test that will resolve the question for me. Null hypothesis. There's no association between gender and coronary arterial stenosis, or there is an association, or alternative hypothesis, there is an association between gender and stenosis. Okay, so I'm going to give you 5 minutes to set that up in SPSS, download the file, and set it up in SPSS. Remember, this is stenosis_smoking.sav. It just happens that we also have gender in here as well. So I want you guys to give that a try, and I'll give you a little bit of a head start. Analyze, descriptive statistics, crosstabs, right? And I'm going to get the outcome presence of aortic stenosis in columns. That's okay, but now the exposure is gender. Does gender have a difference? Okay, so you want to move those in there. I'm not going to do it right now. I'm gonna pause recording, and I'm gonna wait about 5 minutes to give you guys a chance to download that and open it in SPSS, and to set it up and see if you can. And I'll give you another little bit of advice on that. Rather than wait to do things step by step, let's go whole hog. And in statistics, check off chi-square and risk. And in cells, check off observed values and percentages by rows. Okay? And that'll give you a little bit of a head start on that. And like I said, you guys set that up on your own. And I'll wait for, I'm going to pause recording. I'm not going to show you.
This conference will now be recorded.
I presume you can see my screen, I believe so. So I'm going to start recording again. And we're back. And I'm going to go, as you guys tinker with this, if you're still continuing to work on it, just want to show you a couple of other quick things. I'm going to go here and I'm going to go to graphs, legacy dialogues, and I'm going to look at, let's say, I want to look at bar graphs. Okay, and I might want to look at, say, for instance, clustered bar graph. See how that works out. And actually, I'm gonna stay simple. I'm going to go graph, legacy dialogues, and bar graph. And I'm going to say simple. And I'm just going to look at, let's see, what variable am I interested in? I am interested in smoking status. Oops, category axis, okay. And I'll just go ahead and I'm just going to display number of cases. I'm going to click OK. And here's a quick look at what percentage of people in our study are smokers and what percentages are non-smokers. Actually, what quantities of smokers and non-smokers. In fact, if I really wanted percentages, I could have gotten that if I wanted. Let's go back to that. Bar plot, simple. Yeah, if I just check this off instead of cases, it'll actually give me percentages instead of actual numbers of people in the study. Okay, let me go back here, legacy dialogues. Let's do a pie chart and see what percentages are, let's see, how about gender? How much of our population is male? How much of our population is female? Well, it looks like it's almost evenly split, right? Okay, and I think we could have, did I not tell it to display the number? Let's see, graphs, legacy dialogues, pie chart, values, individual cases. Let's do that. No. Okay, let's see, rows, gender, smoking status and columns. Okay, no, still can't do it. No, I'm not doing something right there. Ignore that. Okay, so let's go back to what I originally was going to do. Actually, we could do frequencies. Analyze, descriptive statistics, frequencies, and we can get the frequencies for all of our categorical variables. Put them all in there and get a frequency table. How many people are involved here? So let's see, smoking status. We have 94 people who are smokers, 121 who are not. 40, and the percentage of them, we have the same thing for aortic stenosis. 45% of the population has stenosis. And we have gender, it's almost evenly split, 50%, 51% male, female, and 49% male, and so on and so forth. So we got a chance to look at our descriptive statistics. I just brought this up because when we start talking about, remember, we're going to have a option of either an exam or a simple project at the end of the semester. So one of the things you might be wanting to do is to create a couple of charts or tables to describe the population that you're working with. In other words, the descriptive statistics, even as simple as the frequencies for different categorical variables like males and females, to see if there's a gender difference, if there's an unusual distribution of gender in the population, and so on. Okay, so let's take a look at our what we came here for, which was our null hypothesis, which is that there is an null hypothesis that there's no association between gender and stenosis, and our alternative hypothesis that there is an association between gender and stenosis. And our other null hypothesis, the odds ratio for males and females with regard to stenosis is equal to 1 on null hypothesis, and the odds ratio is not equal to 1 on alternative hypothesis, and relative risk is equal to 1, and alternative hypothesis relative risk is not equal to 1. Okay, so let's take a look, let's analyze this, take a look at it. Analyze, descriptive statistics, get the crosstabs, the hiding place for the information we want. And in the rows now, our exposure is going to be gender. Now, in the columns, the outcome again is going to be presence of aortic stenosis. And in statistics, I'm going to ask SPSS to calculate chi-square and also calculate risk, which is really actually odds ratio and relative risk. I'll click OK. In cells, just for the hell of it, I want to get my observed values and maybe percentages by rows, just because that's kind of informative, right? Gives us the percentage of people that have aortic stenosis for males and females. I'm going to click OK. Our output table comes up, and look at all this information we have. Okay, we have 215 people in this study. There's no missing value, so it's 100% of the 215 are being used for this data. And here's our observed values: 36 have stenosis out of 109 females, and 62 males have stenosis out of 106 males. Quite a bit. That's quite a difference, isn't it? Okay, so SPSS, look at the risk for females. 33% of the females have stenosis, and 58.5% of the males have stenosis. Now this is interesting because of the way we identify males and females. Males might have been 1 and females might have been 2 or something like that. Okay, because of the order we put them in with that number, SPSS put females on top, even though they have a lower rate of stenosis. So now what does that mean for our relative risk and our odds ratio? Well, our relative risk is going to be 33%, 0.33 over 0.58. It's going to be roughly 0.5. That's odd, right? Remember before we had 2 to 1. It's 2 to 1 basically, but our odds ratio, our relative risk is going to come out to 0.5. What does that mean? That means our risk, the risk for females, is half what it is for males. In other words, being female is protective, right? So if we had flipped the numbers and made the males 1 and the females 2, then the males would have been on top here, females would have been on the bottom here, and our relative risk would have been 2, meaning you're twice as likely to have stenosis if you're a male than if you're a female, versus the way we did it here, which means if you're a female, you have half the likelihood. It's just another way of saying the same thing. The only thing is that could trip you up a little bit is it's a fraction less than 1 instead of greater than 1. That's okay. As long as it's different than 1, we can reject the null hypothesis. And in a sense, now we know being female is protective. Okay, so let's see what our Pearson's chi-square is. It's equal to 14 point something for 1 degree of freedom. So 14 is way higher than the critical value of 3.84, which we would have gotten from the table. So that indicates we can reject our null hypothesis. There is an association, reject the idea that there's no association between gender and aortic stenosis, and accept the alternative that there is an association. And what's the probability of being wrong here, of there being an association, being wrong and rejecting null hypothesis, and getting this big an outcome, this big a difference between the expected values and the observed values, if the null hypothesis were true? Well, it's less than 1/10 of 1%. It's less than 0.001. SBS doesn't have an easy way to put in a less than here, but it's never really 0, the probability. It's always going to be, in this case, less than 0.001. Okay, so we reject the null hypothesis for these 2 reasons. What about odds ratio and relative risk. Well, our odds ratio is 0.35. The odds of having stenosis, if you're a female, is 35% of what it is for males. In other words, being female is protective. But we have to make sure, remember, the odds ratio or null hypothesis is the odds ratio is equal to 1, or alternative hypothesis, the odds ratio is not equal to 1. In other words, the risk is not the same. The odds are not the same. And let's see if our confidence interval excludes 1. So 0.201 to 0.610. 1 is not between those two numbers, so we can reject our null hypothesis. How about our relative risk? Remember I said it was going to come out to about 0.5? Well, here it is, 0.565. The risk of having stenosis is about 0.56. It's 56% of what it would be if you were a male, if you're a female. So it's a lower risk for females. And for relative risk, 0.41 to 0.77 is our confidence interval. It excludes 1, so we can reject the null hypothesis. So all signs point to Rome. What is all roads lead to Rome, right? Is that an expression? All roads lead to Rome. Well, in this case, all roads lead to rejecting the null hypothesis. For the relative risk, for the odds ratio, for the chi-square, and for the significance, the p-value, for the chi-square, right? They all agree with each other, which is, typical for them to all agree with one another.
So right now we rejected 4 different ways.
What's that?
Right now we rejected this hypothesis 4 different ways.
Right. In general, they'll all agree.
And is there like a chance one can reject and one cannot reject?
The only place I can imagine that happening is if they're all right around 5%, and one of them gives you 0.51, and the other gives you, but in reality they're really all the same thing. So yeah, they should all agree. They should really typically all agree. Okay, so I think if you were able to get through that, you're able to do what you need, and maybe listen to the lecture. You'll have what you need to move forward with chi-square. Okay, chi-square is going to be important to us because some of the databases I give you that you will be options on doing it. Remember this, I'm not bending your arm. You don't have to do a project. You can just take the exam. The exam will be chi-square and correlation and regression. The other 2 topics we're finishing up the semester with. Okay, so I don't want to bend your arm on that, so you don't have to do a project if you don't want to do a project. But I like the idea of doing a project because then you get an opportunity to just get a raw set of data and now go have fun with it. So I prefer you do that only because it's good practice. Okay, and even if you decide to take the exam, you can always play around with the databases I give you just to see what tests you would use for it and so on. Okay, so take a look at the video. I think we should be in good shape. I'm going to post an assignment for chi-square in the next few days, but I'm going to wait. Maybe I'll wait until after I post the exam on Wednesday because I don't want you wasting time on it right now. Go back over what we've done with confidence intervals, with the t-test, with analysis of variance. Get comfortable with that. On Wednesday, we're gonna, we'll have a review session starting at 5:30. I'm most likely, unless I got another reason to be here, I won't do it here. I'll do it at another location. But I will be on. But it will start at 5:30. So you can log on if you have questions, especially if you're not going to be able to log on. Make sure you post a question or an area of concern in the discussions board so I can make sure to cover it. Then as well. Okay, and then you'll have the exam that you can take then. The other reason I kind of like, you might say to yourself, why don't we have the exam today and start chi-square next week? Because I wanted to give you the weekend to work on the exam. So the exam will be posted on Wednesday. You'll have until Sunday night to complete it. So I wanted to give you the weekend to do it. And this is the only way that I needed to fill in tonight in order to do it. So I didn't want to kill one night. 2 nights on review or exam, so I did it this way. But yeah, we're gonna put this aside for a little while. Come back to it on Monday, next Monday. But in the meantime, on Wednesday, we'll do an online review session. Okay, and again, post questions in the discussions board If you're really shy, you can email them to me, and I'll bring them up during the email. But I like doing it in the discussions board because you guys can have an exchange then as well. And then if I answer them on the discussions board, everybody gets a chance to see my answer as well. Okay, so let's call it a night. And if you since you still have a little bit of time, if you want, you might want to skim through that. I think with the videos, when you go fast forward, you go to look for spots you're interested in. It's called scrubbing. You might want to scrub through the video. I don't want to force you to watch the whole thing, but you might want to scrub through the lecture video just to get a flavor of what else might be on there that I haven't covered here. But I think that you got about 95% of what's on there. Okay, it's a little bit more formal on the video, right? So you get a little bit more of the notation that a statistician would use on the video. But I think we covered the practical end of this, actually using the statistic to demonstrate an association between a couple of categorical variables. Okay, so have a good night, and we'll talk again on Wednesday.